So we're going to resume. We're very excited to welcome Skylar Tibbits, who is a wonderful designer and engineer from MIT. MIT, with whom LUMA and MIT are actually starting a collaboration for 10 years of intense exchange that is going to be, really should be able to bridge high-tech and low-tech together in order to think of how to build and construct differently various forms of technology. And so we're really delighted to have with us Skylar Tibbits, who's, as I was saying, designer and computer scientist, founder of this amazing lab, the Self-Assembly Lab. He's best known for creating 4D printing. He's also the author of Things Fall Together, a guide to the new material revolution, published in 2021. His work has earned him several honors, including LinkedIn's Next Wave in 2016. He's a R&D Innovator of the Year. He was named R&D Innovator of the Year in 2015 and National Geographic Emerging Explorer the same year, among many others. Skylar is going to talk to us about his approach of somehow landscape regeneration almost. Maybe it's not the right word, you'll tell us about that. But at least preservation, adaptation, and anticipation. And so we're really delighted to welcome you here. Thank you, Skylar, for being here.
Thank you. It's a pleasure to be here. Thank you to LUMA for the invitation, and always happy to join. I'm Skylar Tibbits. I'm faculty at MIT Department of Architecture, and I run a lab called the Self-Assembly Lab. It's a lot messier than this if you've been there any time recently. This is like when he first moved in. And the lab really focuses on different scales of work. Some is material-based, quite small scale. Some is all the way up to island scale, so we'll talk about that spectrum. But all of the work is trying to think about how do we build smarter things and how do we build in a smarter way. And we believe the way to do that is the relationship between materials and the environment. Rather than smart systems, meaning robotics and mechanisms and more computing, can we embed all of those capabilities into the materials and into our environment, and so they can have agency, they can have information, they can have sensing, they can have actuation, but in a really like passive or passively active way. So that's what we focus on. But over the years, we've been working on many things. This is what's called 4D printing. It's objects that morph underwater, or auxetic structures that morph with temperature or sunlight, or textiles that transform based on sweat or pH sensing, liquid printed structures that produce inflatables for soft robotics, so you can have pneumatic actuators, or this is a project we did with BMW on morphable car seats, or a lot of self-assembly work. These components come together to build a chair, and every part is unique. They have to find one another and make the chair. Or these are weather balloons that float in the courtyard, and they come together with Velcro nodes to make lattice structures. And so we've done a lot of different experiments, some very much on the applied spectrum, some very much on the basic research spectrum. But what I'm going to talk most about is the end of that video, the self-assembly work. And as the lab's name suggests, we're really interested in this phenomenon of self-assembly, how disordered parts build ordered structures through only local interaction. And all of us are built that way, so all of us are self-assembled. Our planets are formed that way. You know, there's no one out there 3D printing planets, and there's no little like screwdrivers bolting together humans, but anything at the smallest scales from biology, chemistry, material science, and then anything at the geological or planetary scales utilizes the principle of self-assembly and self-organization. But what's really strange is anything at the human scale that we make, think about construction and manufacturing, happens from the other way. It's top-down. Like we have an idea as a designer, and we tell people or robots to make that idea. So that became really interesting to us, like why outside of the human scale is everything built using self-assembly but not at the human scale? And what if we could change that? What if we could tap into this process? So over about 10, 15 years, we've done a lot of experiments. You saw some of them. This was one of the very first ones. In a glass flask, there's the poliovirus, a model of the poliovirus. And when you shake it hard, it breaks. And when you shake it a little bit softer, it comes back together. And this was one of the early breakthroughs where we showed that self-assembly can also happen at the human scale. You know, if you're in biology or chemistry or planetary physics, you understand this principle. but if you work in manufacturing or construction, you probably never utilize this thing. So we were trying to show that it could also be at the macro scale. But most what I'm going to talk about is a project in the Maldives. And collaborators of ours, an organization called Invena, reached out to us. They had seen some of the self-assembly work, and they invited us to go to the Maldives. And the bridge here is because islands form themselves. And so we became really interested in what if we could take all of the knowledge that we've gained about self-assembly and self-organization, and we could apply that to island formation. So low-lying islands like the Maldives, many other small island nations or coastal regions are facing the same thing: erosion, storm inundation, sea level rise. And there's really only two approaches that people take. One of them is to fight nature, build walls, build barriers, trying to resist all of the forces. But that almost never works. At least over time, it's going to break down. Nature is always going to win. And sometimes it amplifies the negative effects. And there's a lot of case studies that have been shown that fortifying cities actually makes it worse. So that's not the solution. And the second one is dredging. And this happens in beaches all over the world. We hear examples in the Middle East, but they pump sand from the deep ocean back onto the beach to rebuild a beach or to build new development. And this is really not great. It's really nasty energy-wise. It kills all of the coral. It's not great for the marine environment. It's not a solution as well, because when you pump the sand, it then just goes away the next season. And then you need to spend hundreds of thousands or millions of dollars to do it again and again. So the sand doesn't want to be there. So in the Maldives, we realized they do the same thing. So they can build an island in about a month. So they'll do this for development purposes. It's really not great, but what we became focused on is that in the same amount of time that they developed this island, 3 smaller islands had built themselves, and these were sandbars, and they show up in a month. This is one of them. When we first went, this is the first place that they took us. It's an island that's about 1 meter above sea level. It's tens of meters in any direction, and the locals will take over the island for a day, and they'll have family there, they'll have parties, they'll go there just for an excursion. These are full-scale islands that show up out of nowhere in a month. So that became the turning point where we realized, like, this is possible. This is what happens. You know, many islands have self-organized. Other than volcanic islands, that's a different process. But in coral-based atolls or sandy islands, the sand is self-organizing into these formations. So the question became, how does that happen? And could we promote that to happen? And this is sort of where the unknown or the unexpected comes in, because this is a system that we very much did not know about. This wasn't our expertise. But even the most advanced people that have been studying this for their whole careers really don't know exactly how this happens. There's a lot of variables, and it's a really complex, like truly complex natural system. So we started to try to break this down. What are the forces, and why does this happen, and when and where does this happen? And our big hypothesis became it's the relationship between the force of the ocean, winds, currents, and tides, and the bathymetry, or the change in topography underwater. And the relationship between that is what guides or erodes sand. And so then what if we could change that topography? What if we could place structures? These would be passive natural structures that then the sand could be guided, almost like gardening in a way, that over time, we're not sculpting it, but over time the sand will accumulate into certain regions naturally. And so how do we deal with this unknown? One of the ways is we study it computationally. And basically our approach is look at it in every angle you can. So one is computationally, and we use all the computational tools that we can think of. This is an example where we're placing structures. Then the bright yellow is where the sand would accumulate, and the purple is where the sand would recede. And we're trying to study how these structures then would accumulate more sand or less sand. Another way is physical experiments. So in the lab, we have several flumes, and we can pump waves, or we can flow current, or we can change tides, and we can physically experiment with it. This is one where we place an object and we pump waves, and then just the waves interacting with that object accumulate sand behind the object. So we change the geometry of the structures and the materials, we change the force of the water, and we try to study how does the sand accumulate in the tank. In this one, we have 8 pumps, and we can turn on and off the pumps. And this is like changing the weather. So in the Maldives, there's 2 monsoon seasons. They're at 180 degrees from one another that roughly change half the year. So we can create one monsoon season or another, or we could change the weather for any place. And then we see how the sand self-organizes to form these different islands. So the physical experiments are really useful because they're real-world physics. It is real sand, it is real water, but the scaling effects are not accurate. The computational models are really useful because we can do thousands or millions of experiments, but the physics is really hard to get. So they have, they have two different advantages. From this work, though, then we started using computer vision and imaging it so that we can build machine learning models to predict how it would move. The example we've been thinking about is if you want a certain structure to emerge, you want a circle to emerge, then what patterns of water would need to flow? Or if you have certain flow patterns in the current, what structures would emerge in that case? But then we started translating that to satellite analysis. So we track the movement of sandbars and islands, and we can then use that to monitor how these islands are growing and changing. Some of the oldest islands where you have the most vegetation, you see they hardly change at all. And then some of the smaller ones, the sandbars, are highly dynamic, tens of meters of movement from one month to another, or they'll completely disappear or reemerge. And so we started to study that, and then now we're building a model that can do predictive analysis. So one of the things we realized is if you have a beach or you have a coastline, there's no weather system like NOAA. In the US we have NOAA, or there's no air traffic control for coastlines. There's no one that will say you lost 5 meters of coast last month, or you're going to lose 2 meters next month. No one's monitoring that unless you're out there physically measuring it or taking drone surveys. So what we're trying to use is satellite images, and then we build up a database of these images, and then we can build predictive models. We say, over the last year, you've lost this much, or you gained this much. We predict this area is going to be the most critically at risk. So we're now building that out of the tank experiments and using satellite images. And what we're trying to build is a global monitoring system. So, that's the vision in the long term, that we want to have the system that's constantly monitoring all the world's coastlines to be able to monitor and predict it. But the most important work that we do is the field experiments. And nothing compares to the field experiments because that's real physics, it's real reality, everything is real. The problem is that it's super expensive and it takes a long time. And so you need to compare that with the lab experiments and the computational experiments and the satellite, and all of those things sort of need to work in concert. So this is a little outdated. We've done now 10 experiments over the past 9 or 10 years. They're different scales, usually tens of meters. They're different locations in the Maldives. Some are reef lagoon flats, some are beach conditions. I'll show you a few of them. 2019, we did a structure that was 20 meters long by 4 meters deep by 2 meters tall. And we place these structures, they're all passive, so there's no pumping, there's no mechanisms inside, they're just a passive geometry. This one is almost identical to that tank that you saw, we were pumping waves. And just over the course of several months, we started to see the sand accumulate. You see the light areas where the sand is accumulating. And then what we saw over the course of the next year is 2 meters of sand. So the sand reached the top of the structure. It was 2 meters tall. The sand started to go all the way to the top of the structure, so we knew we had 2 meters of sand now accumulated in a roughly 2 to 2.5 meter deep lagoon. So we have maybe a half a meter, depending on the tide, left to go to breach the surface. So this was a really big breakthrough for us, and it was the first time that the computational models, the flume experiments, and the field models all were correlating, saying the same thing. So we knew we were onto something. More recently, we did this structure, which is 90 meters across. So those little dots, those are people swimming. And actually, it's like the ambassador to the Maldives and some of the government officials came out and wanted to scuba dive and snorkel around. And so they're swimming. We had just installed it. And the difference here, one of those structures is like the previous one you just saw. So this has 6 of them, and it's 90 meters across. And the reason it's in this shape is because it's omnidirectional. I was talking about the monsoon seasons. We want to make sure that no matter what season, what direction the current is facing, that sand can always be accumulating in the same spot. And this one is really targeting dredging. It's a longer-term need. It's a development question. But we really want to show that you don't need to dredge if you're going to build new islands. Why don't we promote sandbars to emerge? So it's a little bit different. The more urgent need is erosion. I'll talk about that in a second. But then we started to see a lot of sand accumulation, and this is over the course of several months, so very quick. You can see the progression of the same structure. And it's a little hard to see the depth of that, but if you look underwater, again, these are 2 meters tall, and now we have even less space to get to the surface of the water. So that's a person's ankle all the way in the back there. So we have maybe 6 inches. I don't know what that is in centimeters, but it's 2 meters of sand now accumulating. And so we're seeing a very large quantity. And now we're starting to do bathymetry surveys, and we can compare that and have some data. Another approach that we took was a modular, quickly deployable structure. This one we can make 40 meters in about an hour. And these ones, it's like you would have a fleet of these. So if you had a beach or a coastal property, you could deploy them in certain seasons, and then you could move them and take them away, or you could change the direction depending on the storm. So they're really, really light, cheap, easy to deploy, whereas the previous ones would be permanent, and over time the island would then engulf the structure. Then we started to think about all the natural systems that already do this. So mangroves are one great example, and part of this is because of the density of the mangrove network. Basically traps sand and accumulates it, but it also stabilizes the sand. So then what we started to do was make floating gardens. So you'll see in a second there's these like yellow circle gardens that we put out there, and they had mangroves and screw pine and other native species, and they're hovering over the 2019 structure. And the vision here was that the plants would grow down as the sand is growing up. It would promote more sand to be trapped, and then it would stabilize the sand that it accumulated. And so this was an approach to try to use vegetation. I think now looking back on it, one of the challenges with this is that the vegetation takes so long and is so fragile. So there's still a question about how scalable would this, and lots of people are trying to use vegetation on coastlines. So that's one question. But we're really trying, as you can see, in all these experiments, study with different materials, different deployment techniques, different construction approaches, and trying to understand what is the impact in sand accumulation, but also what is the impact in the marine environment. And so we do environmental surveys. The most recent one that we did was a beach condition. So this is at a new resort, and they dredged this whole island. Then they realized, wow, the island is eroding because the sand doesn't want to be there. So then they brought us in to do this, and we made 54 of these units, and they were cast directly on the sand. So we dug a hole in the sand, and then we cast directly into the sand, and then we pull them out, and every one is unique. So none of them are the same. And they have all these nooks and crannies so that the coral can grow, and they have like little fish habitats and for the marine species. And we made this long line of them. They're placed again with this amphibious excavator. So they made 54 in 2 weeks, and they placed them out in several days. They're about a little over a meter by a meter by a meter. This is what they look like when we first placed them. You can see all these kind of nooks and crannies. And then very quickly, the sand started to accumulate. And the sand is now migrating through the structures back onto the beach. So this is effectively doing wave attenuations, like how do you dissipate the force of the wave, accumulate sand back onto the beach, and then provide marine habitat. And this is the first time we brought together the sand structures we were doing with the marine habitat, and I'll show you in a second. We do a lot of work now on trying to study how coral grows with a kind of visitor or human experience. Like we wanted this to be basically an underwater sculpture, underwater garden that they could dive, snorkel, they could have a destination, because a lot of the others were just purely experiments to accumulate sand. We need to bring all the constituents together. Another aspect that I was kind of hinting at is we were trying to think about what are the materials we build with, and as you can see, we've tried lots of different things. But what we started to realize is that you can take local sand and coral, you can fire that, it turns it into lime, and then with lime you add water and aggregate back in, and you get concrete. And this is really an indigenous practice, and many communities historically have used this. It's called tabby concrete, or has different names. And so we're using a similar process. We're now trying to kind of optimize that. We can print with it, we can cast with it, and we make these different experiments. So we've tested different fabrication approaches, and then different chemistries, different geometries and textures, and then we've placed them underwater in the Maldives, and we try to study what grows or doesn't grow on them. And the goal is that now we use this material to build the larger structures. Right now we can only scale it to the lab scale, but the goal is that long-term you could use this, because it creates this kind of net positive where the sand and the coral are being used to build the structures, which is being used to accumulate more sand, which then grows more coral, which then produces more sand. And so you have this kind of net positive, but you also have obviously a positive for the marine environment, because this is made out of the calcium carbonate of the reef. And so we have some nice examples of coral, productively growing on these, and these are all not transplanted, but just natural coral growth. So we're excited about this, but there's still a question on scalability. Now I'll switch gears to show you one last project, to kind of hint at this, and think about that same ethos, like how do we build with the forces of nature, and rather than destroying, can we work with these forces? And this is a project in Iceland, almost exactly the same method, but now we're working with volcanoes rather than oceans and currents. Near the Blue Lagoon and the power plant in the town of Grundavik, there's a volcano that has gone off, I think 8 to 10 times in the past 2 years, and really is threatening a lot of infrastructure in the town. And so what they're doing is they're building big walls, they're fortifying, they're basically fighting the force of the lava. So it's the same kind of challenge. How do you work with this force? It's a massive amount of energy. So what we've deployed now, the first one, I think of this sort of like the very first stages of the Maldives work, where we've gone out and deployed a structure in January. It's basically like a distributed units, and half of them we placed in a location where the lava has hit almost every time. So we know that it has a pretty high likelihood that it's going to hit there again. And the other half we put on a truck so that the emergency management and the civil engineers can deploy them depending on where the lava is going. Like if it's going towards the power plant or if it's going towards the town, they can use these structures and deploy them. And it's not trying to build a wall to fight the lava, but rather it's trying to actively cool it, it's trying to actively guide or tunnel with it. And there's an interesting case study that they saw where there were structures in the landscape, and as the lava hit, these structures started to like move and roll with the lava, and it actually changed the direction, it changed the flow of the lava. And so we're interested in these like very lightweight, quickly deployable systems. You know, you would need tens of thousands of these, you know, in the larger scale, but they can be light, small, they can be combined or aggregated together if you need to build larger ones. So this is the first experiment, and then since January, these are some of the previous eruptions, we've just been waiting and our bags packed, and we'll fly over there and try to document it. And what we're trying to do is understand the interaction of the lava with the structures. So where is all of this going? To me, this is the antithesis. Like, you know, this is how we build all of our cars, our buildings, our phones, our watches, our clothes. It's more and more parts, it's more and more labor, more and more energy, and the key here is that everyone thinks intelligence means more devices, more robots, more components, more functional things, and it's sort of a brute force method that just gets so complicated, takes so much energy, has so much failure that it's really not smart anymore. And this is really like the top-down control method. But what we're arguing for is the opposite, that we need to let systems design themselves. And I was really inspired by what Bas was talking about, and I think there's a lot of examples in our natural world of how we can work symbiotically or harmoniously to not control everything, but allow things to emerge and just figure out where is the right way to dance with these forces. So I think the vision is design is not about control, it's about guiding the unexpected. Thanks so much.
Thank you so much, Skylar. Thank you so much, and it's really interesting to hear you talking about those systems that we need to letting systems design themselves. Are there any questions for Skylar? On peut traduire les questions s'il y a des questions.
There's one.
Grégory.
Thanks so much for this very fascinating metamorphosis and kinetic approach. Did you connect with local knowledge of how, sand was forming, was coming out, etc.?
Yeah. So I was talking about Invena was the organization, and they're from the Maldives. And actually, the grandfather of Hassan, who's the person that we collaborate with, the grandfather is a historian in the Maldives, and he famously went to every island of the Maldives and documented and wrote a big book on it. And so he passed away, so we couldn't talk to him, but we talked to some of his friends and some of the elders. And and this really inspired a lot of the beginning, because they didn't have dredging at the time, obviously. So what they would do is they would place coral boulders and place vegetation in strategic places, and over time the island would start to grow in certain directions. And obviously this would take various seasons and years, but they could help guide the island to grow in certain ways or connect between two islands. And so that became the inspiration, is like, okay, this has happened in the past, but now how can we apply all of the knowledge of computation, of flume experiments, of field experiments, and latest materials, deployment techniques, like how can we bring all of that to what they already knew was possible? And really what we're up against is time. Because unfortunately what they will say, the government will say, or the resorts will say is, well, I can make an island in a month. How long does your process take? And that's really what we're up against. And it's sort of unfair, because it's like, sure, you can make an island in a month, but then your island disappears next month. with dredging, but they see it as that. And I think we need to have a kind of different perspective and so one of the things we're thinking about is how do you place structures that allow you to then build or open as soon as you can, but over time the beach then fills in between, or like finding these games where it's not just about like pure efficiency, but you can still use natural approaches and not just totally avoid that challenge, but really kind of work collaboratively. Yeah.
Thank you very much for your talk. I was wondering, what is your relationship with the history, philosophy, and science of complex systems and its connection with self-assembly?
Yeah, I don't know if we have a relationship with the history and philosophy side of it, other than, one of the reasons I got into this 20 years ago or so was I was really interested in how computation was changing design, and at that time it was all about like complex systems and cities and Santa Fe Institute and like studying self-organizing systems in nature. And if you look at the history of computing and the like research in complex systems, they're really intertwined. And a lot of the people from computing started, even if you look at Turing or von Neumann, like early pioneers in computing, they started to go into like chemical morphogenesis and like really interesting complex systems, or like Game of Life, early like Conway's Game of Life started to get into these. So I come at it from that angle, and that's how we got into these. But we don't really study like true complex systems other than we work with complex systems. Like our lab isn't really about complex systems. We look at self-assembly and self-organization, which is not always truly complex, but weather patterns and the geomorphology of landscapes and lava flows and all those are actually truly complex systems. So we sort of, work hand in hand with them. History and philosophy, we should talk later, because that's definitely not in our world, yeah.
That's what we hope we'll do with you.
Exactly, let's team up.
Thank you for that brilliant presentation. This might sound really ignorant, but I was thinking about the ways in which what were once the islands that made up what is now Mumbai were joined together by placing these concrete tetrapods and reclaiming land, which is, I believe, a quite common practice. Singapore has also done it and so on, Hong Kong. So my question is really about the ways in which even those forms which are as, quote unquote, artificial to that particular environment actually get taken over by all kinds of sea creatures, including, for instance, flamingos nesting there amongst sewage and so on. So there's a line of, argument in ecology that looks at the ways in which what you get are these kinds of syncretic environments. So what would you say to that point of view?
Yeah, and talking with the Tour du Valot people here, there's man-made infrastructure and dikes and groins that then over time started to get broken down and erode and actually became very productive in sand accumulation and like effectively the resilience came back. In a way, I guess I think of that as like nature always wins, and in that case they were trying to fight it, and over time they lost the battle and nature came back. But it also is a really interesting positive example that with kind of just the right interventions, positive things could happen. We need to be careful that we're not too heavy-handed, and you probably can't just say, like, let it do whatever it wants. Like, we also often need to live and, be part of these ecosystems. So we need to find that very delicate balance where we are going to intervene in some way, but how can the things you intervene have as positive effects as possible? That's like kind of the threading the needle. The tetrapods are an interesting one, though. Actually, tetrapods are really fascinating because another part of our work is about granular jamming. And tetrapods, they are individual units. They act like a solid when they're hit with impact, but then they also can flex and move. And so that is an interesting one. And as you said, there are a bunch of examples of them being taken over with marine life and potentially providing a net positive. I think the problem is that, especially like since the Industrial Revolution, we have had this mentality of like we are more important than nature, and we can stop nature, and we can resist it and fight it, and we exert control over it. And especially in the US, like the Army Corps of Engineers is notorious for this, like building groins and dikes and breakwaters and jetties and trying to fight it. And many of those have had very negative consequences, like houses that were just barely eroding, like completely went underwater after they built these structures. And so I think there was like a misunderstanding or a kind of ignorance that they thought they understood everything and we could fight it, and actually it had really negative. So we need to not do that again. And I think that's where we're trying to take this kind of multifaceted approach, collaborate with experts in all these different fields, study it from every angle we can. And everything that we deploy, we could take out. And everything that we deploy, we try to make it so that it can adapt over time. So you hopefully aren't going to have these other negative consequences, but you are intervening. So you're one step closer to that rather than just doing nothing. And hopefully the things you intervene have positive effects.
Thank you, Skylar. It's actually very interesting because, as you were just saying, instead of thinking of building a protection to protect the island from the wave, you somehow use the strength of the wave, so that it can work for you instead of working against you.
Yeah.
And that's a very interesting principle in terms of like the architecture of the unknown. Maybe it's a principle that we can think of, and notably with all the work you do.
And when I was there, just really quickly, we went to the sandbar, and I started to think like this is actually the future of building in coastal cities. The sandbar, not Miami, Male, New York, like any of these coastal cities where we have concrete jungles and we fortify it. Like we think that that's the future, but actually these sandbars are growing, changing, fluctuating, dynamic. That's much more resilient than these hard infrastructure. So we really need to learn from that.
A difficult question, but do you expect some side effects that are, like negative so far? Or, I mean, because you showed something that is very seductive, but I mean, in all honesty, do you already see that there's some parts that are?
No, we haven't seen any negative effects on the marine environment. Some of our structures haven't worked. So there's several, I mean, we've done 10 of them. Most of them haven't worked. The ones I'm showing you are the ones that have been successful, but there's lots of things. I mean,
they're the best of the structures.
There's like hundreds or thousands in the lab that didn't work. I mean, like literally most things we do don't work. And slowly we're building up structures that we know have worked. And now we need to try to make sure we study it and how can we translate it. But so most of the failure is on our side, like our things aren't working. But no, we haven't seen negative. If anything, it's been like incredible to see. We'll place a structure and the next day we'll go back and there'll just be like thousands of fish in this thing.
Wow.
It's really strange because it's this reef flat. There's nothing, it's just like completely flat. And so they have nowhere to hide. And then when you place these, especially the ones that have like nooks and crannies and undercuts, they just like flock there and then they hide. And then all the fishermen come out there and they stand on top of our structures. Like it's a whole nother problem. And then there's sand pirates that come and they steal the sand. Like seriously, they dive down and they steal our sand. Wow, so that's a whole other problem we have to deal with. But
that if we stop using concrete, people will stop stealing the sand. So that's another bridge of connection with the work that needs to be done in terms of construction. This is perfect. You made a connection with the very first day. There was a bioregional assembly that was trying to see how we can get only buildings in concrete so that pirates stop stealing the sand in the Récif that you do. Wow, I didn't expect that connection. So thank you for this, Skylar.
Yeah.
Et nous avons maintenant le plaisir, je change au français, donc if you need a translation, do not hesitate to get your headphones, mais